Questions on what has passed so far? Okay. Okay, I said I don't have a slide for this. In the programming course, there's a long history. I'm not going to be able to do the history justice, but I will say the following. Person who definitely popularized GP as a moving force behind it is John Poza, roughly in 1992, where he introduced tree-based GP, even though there was maybe some other papers on tree-based GP before then, but he's basically responsible for creating the field. There's earlier people who've done it. Okay. So, just like we've thought so far, genetic programming is a type of genetic algorithm. In GA, the genotype is a binary string. The phenotype is a set of numeric parameters. Genotype is a tree for this kind of GP, and the phenotype is a computer program. You can, of course, imagine more complex representations. Okay. Just like for permutation, we can perhaps do mutation or crossover literally, where the idea behind mutation is we're doing some sort of local search, and crossover, either we're doing a needle mutation or we're hopefully combining building blocks between two separate systems. Okay. So as we saw with the Mondrian painting, we could represent that painting. The representation turned out to work out as a tree, and expressions, for instance, arithmetic expressions, can be represented in a tree-like form. So here we have infix notation, where, for instance, the plus comes between the operators. But an option would be to represent this numeric expression rather than our standard notation as where we put the operator before its operands. And once we do that, when we put the operator before the operands, the tree-like structure of an expression becomes much more clear, where, for instance, plus, like vertical here, is now at the root of our tree. So here I just translate this expression to that expression. Now let's do an example. Or furthermore, we can go ahead and we can take that previous expression. Is there anybody who hasn't seen the representation of expression as a tree before? Okay. So I will just go ahead and do that, but it's not everybody's done computer science. This is part and parcel of computer science. Computer scientists love trees, even if MATLAB doesn't love trees. Okay. So we've taken this expression plus sine x square root of xy, and we've rewritten it in prefix. So plus has two operands, the thing on the left and the thing on the right. So plus, and then here on the left we have sine x, and on the right we have square root. Sine is on the left, and its operand is sine x. So we can see plus sine, maybe whether this should be on the left or right, I don't know. I'm not concerned about that issue. Square root. So now we're going to take the square root of left-hand side. Square root. We're going to represent plus to be plus x squared plus y. So here we have plus. Here we have the exponentiation. Then we see the x squared and the y. So we can represent a given expression like a tree. Yes?
Wait, would this only represent two terms?
Two what?
two terms in the expression, or would it? Could you?
So you have multiple options here. Well, in general, if you wanted to have a function that took 3 operators, you could have 3 branches.
Okay.
And if you have things like plus and time, let's just say the number of branches on your tree corresponds to the arity of your operator, which is the number of arguments that it has. Okay. So we've shown infix notation as a tree. Okay, for some of you this will be easy, but others of you, I suggest just to practice, we all take a moment now to draw the tree representation of these representations, as well as give an example of the prefix form. And there's arguably more than one correct answer for the second one. And if you have a question, please raise your hand, and I'm glad to come around and make observations.
So this right at that side, so it's like plus and 5 and 2 and 8.
Yeah, that's perfectly correct.
Okay.
Just check it fast.
Except you have that X in the first one, but if you, I would maybe switch it and call the X an A, but, the same thing.
A, my bad, it should be. Yeah, that's what I mean. I just misread it.
So from that side, well, you do the squared, but would you say that whatever's there is squared? What would you say?
No, I would use the exponent with 2 operators, because the exponent is an operator having 2 operands.
So the operand would be
2. So write the tree and also write it in infix, or in prefix.
The second one.
Yes, second one. So there's 2 reasonable interpretations, at least, to the second one. So that's that interpretation.
Thank you. I gave you from computer science. Just compilers.
That's okay, right? Yeah. How about the so this is the infix. Yeah, okay, that's the infix one. That's the prefix one. Is it like this is the infix one?
Function like
Yeah. Absolutely.
You did the interpretation that nobody else has done so far. But, it's a very natural way to do it, especially if you're more mathematically.
tree form at the moment.
Yes.
Thank you.
Is this right for the what's it called, the prefix form?
The prefix form.
You know, like plus and then it's two arguments
Yeah,
like that.
Yeah, how did we do it under the examples? Let's see. Yeah, you
Shouldn't that be like a comma?
the plus should be here. Well, we're just using space as a separator. And
Because I've got like the plus one actually on this and then that separate.
yeah, so I mean, just if you look at the previous example, you know, there's other notation there, there's a plus there.
Prefix.
Is that right for the exponent?
Yeah, the exponent is right, and the
Okay, cool. Thanks.
It's fine with me. Yes, you know, sometimes I'll comment on that in a moment.
I just checked my arithmetic algorithm so far. For 100 cities, I was averaging about 110,000 a year. So
Pretty
slight,
large,
yeah.
large. Something's gone wrong.
Okay. I was getting 25 on the 48 then.
How much?
25,000 on 48.
Pretty large.
Is it?
Pretty
Okay.
large. Much better. So those would get low marks.
Okay.
Very low marks.
Okay. Fair enough.
This is genetic programming. Yes, you're more mathematical. Okay, let's go ahead and write down potential answers. I saw tons and tons of correct answers, so I think most of you get it. So doing this in infix, we have plus, we have our and we have times for 2a, then we have, we're adding it to exponent b squared and close off everything. So this would be infix, the tree, plus is our operator, and we have a times, and we have a 2. A is our terminal. Here we have an exponent, we have a nice balanced tree, and we have a b and a square. Square root, so we start out, actually I'll do the infix first, we do plus, we do square root, where we take a single operator, then we have times 2. So some of you have done it with 3. I'm going to just do it another way. I'll just put times here, and I'll put x, y. The quick comment being, I'd be just as happy to see times 2xy, but one time, sometimes I have one of those math students in class are like, what do you mean times with 3 operators? Times is the multiplicative operator in the real field, and it only has 2 things. They get very upset that just computer science, just times. It can take 1 thing, it can take 10 things, it can take 0 things. Let's not be picky. But some people really do like times to have 2 arguments. If they like times to have 2 arguments, write it like this. But if you kind of a flexible computer sciencey type, put it with 3 arguments. It doesn't really matter from the aspect of programming. Okay, so we can represent it either way. There I've done it as a 2-argument function, but some people think of it as a function with as many arguments as you want. Okay, so that's times. I did the times. What else is going on in this? So we did square root 2 times x, and then we just need a y. And we're done. We'll do 1 tree, because it's
And you know whether you should bracket the first or the second, you know, there's more than one way of, you know, interpreting the rules of precedence. I think that's the second expression. But I saw nothing but right answers, so I think you all get the idea. Questions? So it's kind of clear we can generalize this to any degree of nested arithmetic statement. Okay. More generally, you can imagine things other than plus, times, minus, and exponentiation. We're going to differentiate. Notice in this picture here we had these things which kind of look like operators, and at the end we had colors. When we did these arithmetic expressions, we had numbers on the bottom, and we had kind of arithmetic symbols in here. Okay? So we can specify the bottom part of the tree, the things that are stopping the branches we'll call terminals, and the inside will be functions. The functions are always operating on the terminals. There's many possible terminals and function sets. What to do if you want to have a mixed set of terminals and functions is not so clear. So you can imagine our functions could be, for instance, you know, plus, minus, divide, and times, and we might just have as terminals some numbers at the bottom, or maybe some variable representing an input. Likewise, we could have and, or not, and these might be variables that took on true or false, doing logic on them. Maybe we're going to have a slightly bit more of control in our thing. Maybe we'll have an if statement or a do statement, like in programming. These maybe you say you can have more complicated function sets. So when Koza came up with GP, one problem which people were very interested in classical artificial intelligence were planning problems. You know, how do you plan out a sequence of actions and do a sequence of actions? And coming up with good ways of planning is a classic problem in artificial intelligence. And the classic toy example world would be to solve planning problems in the block world. And so one way that Koza got people excited about GP is he published some papers where he showed genetic programming applied to a bunch of different problems, and showed how you could use genetic programming to come up with solutions to these problems. So this is a a toy example, but showing how it's like a thought experiment, much like I forgot to hint to Nolan, is showing that yes, you can use genetic programming, even though this is completely impractical, to do a little bit of planning in a blocks world problem. Because previously people had been doing lots of planning with logical inference engines and kind of theorem proving engines. He wants to show that, oh yes, you can kind of evolve a planning method. Okay. So we've distinguished what we mean by terminals. We've distinguished what we mean by the current stack. We've distinguished what we mean by the, sorry, what am I talking about? I'm starting to try to speed up, and I'm sort of going automatic. Terminals. So we have the terminals and we have the function nodes. So the terminals in the block world will be this function. We'll see how this works with the demonstration, which this terminal says current stack. If you saw there was some blocks in the previous picture, this will be the name of the block on the topmost of the stack. Okay? Top correct block is the name of the first block on the stack, which isn't out of order. The next necessary is, if you don't have it, what's the name of the block that would be immediately above the block that's on the top of the stack. And if you have the topmost block here, somehow you get a false or something. Okay, so these are three terminal functions. Did I jump slides? No, this is. So we haven't discussed how the algorithm is going to work yet. So these are the terminals. Here's the inner slides, the inner operators. One operator was move to stack. So what it does is, if a block is on a table, so just remember the picture is the stack is what I'm building. And the goal is to spell universal in a vertical column. And these are things on the table. So move to stack is a function which basically says if block X is on the table, move X to the top of the stack and return true, otherwise it returns false. Move to table is if block X is somewhere in the stack, move the block at the top of the stack, whatever it is, to the table and return the value true, otherwise return false. Okay? Current stack. This is the name of the top block on the stack, or false if the stack is empty. Sorry, I'm going back again. Trying to go too fast and I start making mistakes. Equal. Equal returns true if the two arguments are x and y both return true. Not returns false. I mean, an obvious logical not. Do until is an interesting one. It keeps doing x, whatever x is, until y returns the value true. Okay. So we have a number of functions in terminals. Learn program. So common thing in genetic programming, kind of like what is another thing is rather than have a fitness function that kind of covers everything, is you have a bunch of test cases, because how you test the fitness of something that does something relatively complicated, you can't give it a bunch of examples and hope that it generalizes to all the cases. So the goal was you wanted to build this thing which would always spell universal, and ran it on some 166 test problems, and so using a population of 300 programs, found this following program after 10 generations, which had 100% fitness on these 166 test problems. Let me show you some intermediate. Here's some simpler ones. So this is a very simple program that basically had a fitness of 1. This is a slightly more complicated program that had a fitness of 4. This other one is basically the bottom part of this. Now I want you to take a moment now and try to figure out and ask questions, if you have questions, why this particular piece of code solves the block problem. Well, the goal is to solve universal, to be able to spell universal, no matter what combinations of blocks start out in the stack and what combination of blocks are on the table. So somehow this little piece of code will always solve universal, and what was neat was that Koza didn't write this code himself. The genetic programming system came up with the code. does this work? Figure out how it works, see if you can figure out what the test cases are doing and why they're doing things partially correct, why they're solving some of the test cases. The idea is that you have some test case and the fitness of your system is the number of test cases you get correct.
By the understand the program, because does it keep running until it returns true? This equality.
Yes.
I don't see these with true. That will be problems.
Yeah, so because these two things and this will keep doing this until it's true.
But don't you need until outside this with the true?
No.
Outside?
No, because it tries to evaluate this and it tries to evaluate this, and the process of evaluating this keeps running this path until it finally finishes.
Right.
Okay, if you understand how the code works, just so I know how people are doing, raise your hand. Okay, if you understand how the code works and you're willing to volunteer to explain how it works, raise your hand. Excellent, we can move on. Thank you. Okay, you're selected. How does this code solve the block problem for us?
The two do until functions.
Okay, so we first get this equal, which it tries to evaluate, and one issue is unlike some cases, the order in which you evaluate things matter. So we assume we evaluate the first thing first, and what does this do then?
The only way they both return false is by having the correct word.
So we do this until this is true. And so what does this do?
It moves to the table, the current stack.
So the first thing, we move whatever blocks on the stack to the table. So let's pretend there's something there. And we do it until this statement here is true. And when is this statement true? So we keep doing this until this is true. So the overall thing is we do this until we've taken everything off the top of the stack. Okay. And then what happens here?
You put the next necessary block into the stack until you have no next blocks.
So it does the parallel thing. So now next necessary is the next necessary block. The stack is completely empty now, and so we don't have to worry about putting things out of order. So we move to the stack the first thing which is necessary, and then we keep doing this until necessary returns false, and only return false once all the blocks are things. So it's kind of easy to see that if you take all the blocks off and then you keep adding the first correct element, you will correctly evolve the thing. So commenting quickly on here, I guess if you're only one away from having the correct thing, this one is correct on that case. Every other case it's not going to be correct on. This one you can see that the equalists aren't doing anything. They're just placeholders for the action happening. And this one, if there's some combination of 3 or less blocks needed, you first move the next needed to the top, the next needed to the top. So if you have everything correct except the last 3, and or you have not the last 2 or the last 1, it gets it correct. And this is just a subset of the previous one. So if there's nothing on the stack already, this would do the correct thing. Okay. Okay. Let me comment on the coursework. So we haven't gone in all the steps of the GPU, so let's okay, the GP is the second part of the coursework. For those of you who aren't computer science people, erase this in here. This programming can be a challenging programming task if you haven't programmed something with trees yet. So I encourage you to start writing routines on trees. Is kind of tough if you don't have computer science background. Okay, so now our operators are and, or, not, which we're all familiar with, and if. Let me explain how if works in this context. if we'll take 3 arguments, it'll take if x, y, and z, and basically if x is true, the result is, I want to write it as a tree. If x, y, z, if x is true, then y will be the result of this. If x is false, z will be the result. Okay? So that's what if does. And our terminals for us correspond to 1 and 0, where the interpretation of 1 is true and the interpretation of 0 is false. And for those of you who've done a little bit of electronics, your aim is to evolve a logic circuit, which is a classic piece of electronics called a multiplexer. And let me explain to you how a multiplexer works. Okay? So the multiplexer, let's do a 4-bit, a 4-line multiplexer. A 4-line multiplexer has 2 address bits to address a line and 3 data lines. I mean 4 data lines, D0, D1, D2, D3. And the idea of a multiplexer is that you imagine that information is coming in on one of these data lines. You want one of these data lines to be selected, and the way a data line is selected is by the address here. How does this turn into a Boolean function? Truth value. So the idea here is these 2 bits select the address. So for instance here, this is 0 in binary. So what should be the outcome is D0. Okay? So
D0 is 1, no?
No, D0 is not necessarily 1. The outcome has to be whatever is at D0.
As A0 and A1 is equal to, are equal to 0, then D0 is equal to 1, no?
No.
In the explanation, it's not what it's written.
Let me read the explanation.
No,
This
the output
explanation-
equals D0.
Because the explanation is to say, like, for example, A0 equals 0.
The problem is to find a program that will return the value of the D terminal that is addressed by the 2 terminals. Okay?
And then they give example.
So, for example, if A0 and if A0 is 0 and A1 is 1, the address is 1, and the answer is the value of D1. Okay? So here, the value of D0 is 0, so the outcome is 0. If instead we had this example, and it doesn't matter what's in these bits, I'll put star here because it wouldn't matter. The outcome is always 1, because that's when it's at D0. So for instance, 0, 0, 1, 1, 1, 1, or the output's still 1. Like if I now had for instance 1, 1, 0, 1, 1, 0, what would be the output? 0, because this is addressing 3 and the output is 0. Okay? So what you need now is you're going to evolve a circuit that computes this using the and, or, not, and if operators. Okay? So on the and, these will be the operators. Your terminals will be A0, A1, A2, A3, D0, D1, and perhaps 1, perhaps 0. Okay. Now, so what does a typical program look like? A typical program.
So why the 1 and the 0?
You don't have to put fixed logic values.
Oh,
Just
okay.
maybe you can, maybe it makes it easier, maybe it doesn't make it easier. It's like including true or false. So let's look at a typical program. So a typical program might be not, I'm just making up a random tree. Another, then it might be and. And's going to take 2 arguments. Maybe it gets an A0 here. Maybe this will then be an if, and maybe if will be D0, A0, D1. Crazy. This is going to do quite terribly. It's pretty hard to do worse than 50%. But now if you look, so what happens? So we're going to have 64 test cases because there's 64 possible inputs. And the fitness of a program is how many of these 64, because there's 2 to the 6 possible inputs, i.e. we have 64 different binary numbers of 6 bits. And what it needs to do is it needs to correctly classify, and the hope is that it can do good. 50% is trivial for any network. And so this program, will go in, it'll put in your test case. This isn't going to do very good because it only looks at a couple of bits. It doesn't happen to touch all of them. So there's no way it's going to get all 64 right. That's it. That's your goal. In terms of expectations, I expect, in general, it's not trivial, but the 64-bit problem isn't that hard. Most of you should be able to build a GP that successfully evolves the 64-bit case. It's significantly harder, I'll answer your question in a moment, the 11-bit case, which is we now have 3 address lines and 8 data lines. Okay, I don't, typically, not every program is going to be able to evolve a multiplexer that solves that. What's your question?
So first, on the side, we need to find an algorithm that will give all the true answers. So you find all the legal answers.
You're going to have to figure. So as part of your genetic program, you're going to have to generate the 64 test cases to evaluate the fitness of any given tree that you're going to evolve. Okay. So you have to be able to write this piece of code too. Other questions? The final problem, part 3, is an extremely difficult thing. It's very hard to make much progress on it, but I'll be curious to see what your code does. That's why it's only assigned a few points. Okay. I am at time, so we'll have to come back to genetic programming at another point. Okay. I don't know who the lecturer is next week, whether it's going to be split or not. I expect Chris Watkins will be lecturing. Otherwise, maybe I'll be lecturing, or maybe it'll be a combination of myself and Chris Watkins lecturing. I can tell you a little bit more about GP, and then we'll see how the